So hello everyone, we are the Sulfate Attack group. I'm Michael. Our other group members are Lee Shun and Evan. And we were tasked with making two concrete samples that performed well and poorly against sulfate attack. So this is for a concrete durability class at Oklahoma State University. So what exactly is sulfate attack? So there are two types, chemical and physical. And for this project, we are going to try to get chemical sulfate attack in our concrete. So that's when sulfate salts destroy the cement paste and react to form a new expansive compound. So for this video, we used sodium sulfate, but this type of attack involves sodium or potassium sulfate. So first, the tricalcium aluminate is attacked. This unhydrated cement compound is initially found in Portland cement. One of the first preventative measures to stop this is using type 1 or type 2 cement for low sulfate or type 5 for high sulfate. However, assuming that you do not have protection from this, the tricalcium aluminate will be attacked and transformed to etronite, followed by the calcium hydroxide and the calcium monosulfoaluminate. So for our samples, we decided to create 4 different mixes. And we were hoping to test how different cements, the addition of slag, and different water-cement ratios affected chemical sulfate attack. So we made 1 by 1 by 10 rods to test for length change and 4 by 8 inch cylinders to test for resistivity, mass change, and to do some visual inspection. We weren't able to get really good length change, resistivity, or mass change measurements, so this presentation will be on visual inspection. And our samples were stored in a solution of 5% sulfates by mass, that is Na2SO4. And we also made some control samples that we stored in lime water in the fog room just to see the differences of the ones that were exposed to sulfates versus ones that would not be exposed to sulfates. So this table shows what we decided to do. You can see we have some that were 0.45 water cement ratio and contained slag, and we also used type 1/2 cement, and they were stored in sulfates. Then we also did a similar mix with 0.55 and slag. Then we did the same thing, 0.45 water cement ratio and 0.55 water cement ratio, but these two used type 1 cement rather than type 1/2, and they did not have any slag in them. We also made 2 control bars, one with a 0.45 water cement ratio and one with a 0.55 water cement ratio. They both contained type 1/2 cement and slag, but rather than being stored in the Na2SO4 solution, they were stored in lime water. So here's our samples. This first one is a visual inspection of the 0.45 water cement ratio. So you can see the sample on the far left has no slag in it, and there's quite a bit of surface damage. There's a big circle there showing the worst spot, really. And then the 0.45 that contained slag that was stored in the sulfate solution has a small amount, but not nearly as much as the cylinders that did not have any slag in it. And then on the right, we have the control, which was stored in the lime water. It has no surface damage at all. So next, similar, but the 0.55 water cement ratio. And you can see the top of that left cylinder has a lot of surface damage to it. And there's a little bit more throughout that cylinder, but it's mostly there at the top. While the 0.55 that has slag in it does not have really any surface damage at all. It has a little bit, but not much. And the one on the right is the control, no surface damage at all. It was stored in the lime water. And both of these two images were after 12 weeks of exposure. So this is a close-up view of that 0.45. This is just the one with slag versus the one without slag. They were both stored in the sulfate solution. And you can see on the left, just all over that entire image, there's surface damage. That really the whole thing has lost some of its surface. While on the right, there's not really much surface damage. There is a little bit, but most of those voids are just from the mixing process. So the next thing we looked at was the bar images. These are after 12 weeks of exposure. These are those 1 by 1 by 10 bars. And you can see for the 0.45 water cement ratio, the bar on the top has a small amount of surface damage. You can see the circled areas where the surface has kind of almost spalled off, fallen off. And in the bottom of the 0.45, there's not much surface damage, but there is just a little bit. While the 0.55, there's a huge chunk taken off the surface where no slag is, which is the top image. And then the bottom image, there's not much change. And then, as you can see in the control bar, no surface has fallen off because that one wasn't exposed to sulfates. That's in the lime water, and you can see nothing's happened to the surface of that one. So this image shows the container that our samples were stored in. So that water is that sulfate solution, the Na2SO4. And then you can see almost like a powder that has fallen off, and that's what's sitting in the bottom. And you can see after 6 weeks, there's a decent amount that's fallen off the surface of the concrete. Well, after 10, that amount has increased, and then at week 12, even more has fallen off the surface. So let's take a closer look at that here. You can see on the left, that is just some of that powder that we scooped out, and that's before it dried, and then we let it sit out for maybe an hour or so and dry out, and you can kind of see those individual particles better on the right. And when you felt this, it had a bit of a sandy, silty type of feel to it. So for a conclusion, we found that the surface of the concrete will scale off when exposed to sulfates. And when you use slag and type 1/2 cement in combination with each other, they help protect against that scaling off of the surface. They don't do a perfect job because you can still see some that scaled off, but it is significantly better. And we also found that all of the samples that were stored in lime water did not deteriorate at all. So thank you guys for watching.